Hello and welcome back to Historical Geology. Today I want to do Chapter 16 on the Cenozoic Earth history, primarily the Paleogene and Neogene periods. We'll see that this Cenozoic era is divided into three periods. And so during this Paleocene time, the earliest epoch here, we're seeing the adaptive radiation of mammals. So mammals really take over because all these ecological niches have been opened up since the extinction of the dinosaurs. Toward the end of this Paleocene, we do see this thermal maximum where temperatures are really warm. In fact, we call it the PETM for the Paleocene-Eocene thermal maximum. And what's happening here, we see an increase in greenhouse gases, primarily carbon dioxide and methane gases. And so we see really high sea levels during this time. Shortly after the Paleocene into the Eocene time, we see the radiation of whales begin to move back to the ocean and become adapted to live in the marine environment. By the time we get to the Oligocene time, the development of the San Andreas Fault, San Andreas Transfer begins during this time. By the time we get to the Miocene here, in the Neogene period, we're going to be seeing the uplift of the Sierra Nevada. We're going to see silica-rich grasses develop, and we start seeing large grazers, herding animals, eating those grasses that can take advantage of those grasses. By the time we get to the Pliocene, we start seeing the Isthmus of Panama develop. Mammals move from North America to South America. And really the North American animals, we'll find from chapter 18 that they're mostly placental animals. And those placentals, as they move to the South America, they overtake the marsupial mammals. And so there's a whole family of marsupial mammals living in the southern hemisphere, and they really can't compete with the faster placentals. And so there's an extinction of some marsupials in South America. The Pleistocene epoch begins the Quaternary period, and this is also known as the Great Ice Ages. Several advances of the glacier. So here we're looking from around 2.6 to 11,700 years ago. So it's really a long period, and during this period there were glacial advances and glacial retreats. And so obviously this Pleistocene we're going to cover more in chapter 17. And then finally we get to this really thin region here, which is called the Holocene, or recent. And that really started around 11,700 years ago. Glaciers retreat, global temperatures warm, and we really see a change in the pollen, more from cooler climate species to warmer open grasslands type species. So we really see that in around 11,700 years ago. We know more about the Cenozoic for three reasons. One is we see these Cenozoic deposits near Earth's surface. Two, they haven't been altered. And three is that contain abundant fossils. And not just bones and shells, but also microfossils like pollen. And pollen really is a clue to what's going on with climate. This is a picture near Santa Barbara. In fact, Santa Barbara is right over here. So this is the Santa Ynez Mountains. And this is right near Gaviota State Beach if you're driving along Highway 1 here. We took some students up there and we're looking at some of the sandstones here. And also note that these sandstones are steeply tilted. Remember the principle of original horizontality. These were once deposited flat. And in the last 5 million years, these sandstones have been tilted very steeply with the uplift of the Santa Ynez Mountains and the whole transverse ranges here in coastal California. Other things that are going on by this Eocene time, we see that the Atlantic Ocean has widely separated. And we do have a mid-Atlantic ridge that develops, and it's very symmetrical right in the middle because Pangaea is broken up. Africa and Europe are moving eastward, North America and South America are moving westward. But when we look at the mid-oceanic ridge in the Pacific Ocean, note that it's not in the middle of the ocean, it's off to the east side. That's what we call it, the East Pacific Rise. And it's asymmetrical because as Pangaea rifted, both North America and South America are moving westward, and they're overriding that ocean plate that was on the east side of this mid-oceanic ridge here. Now in the East Pacific Ocean, subduction of the Farallon plate and the Nazca plate. So if we think about what those two are, so the Farallon plate, well, it's pretty much gone because remember in the early Cenozoic era, this East Pacific Rise, or North America, was farther east, and so this East Pacific Rise was a mid-oceanic ridge, and there was a plate on the east side of this mid-oceanic ridge. That's called the Farallon plate. In fact, the Cocos plate here and this little Juan de Fuca plate up here off of Northern California, Oregon, and Washington, these are the remains, or what remains, of that once large Farallon plate. And then the other plate that they're talking about here is a Nazca plate. So that one's still here, and the Nazca plate subducting under South America into the Peru-Chile Trench. We also see the collision of India with Asia around 42 to 44 million years ago. We also see the northward movement of Africa and the Arabian plates to close that equatorial seaway, the Tethys Seaway, and hence we start uplifting the Alps, the Apennines, the Pyrenees. So all those that we see in anywhere from Europe all the way through the Himalaya range and Southeast Asia. And the last thing we're seeing here is this Red Sea and Gulf of Aden, where enough rifting has occurred where we actually develop a mid-oceanic ridge. So the Gulf of Aden is right in here, so there's actually seafloor in there, and then the Red Sea is up over here, so there's a mid-oceanic ridge and seafloor in that region as well. We're beginning to see the rifting of East Africa and developing that East African rift. That also happens toward the later part of the Cenozoic. So during the Cenozoic, there are two orogenies that are important. The Alpine Himalayan, and then the Circum-Pacific belt. Think of that like the ring of fire. And so within that Circum-Pacific belt, there are these orogens, and orogens are smaller segments like the Aleutian Orogen, the Aleutian Islands, the Coast Ranges, the Andes Mountain would be segments of that much larger Circum-Pacific belt. So when we're looking at this Alpine Himalayan orogenic belt, it goes really from Spain, which includes the Pyrenees Mountains, through the Mediterranean, including the Alps. In the Middle East, it goes through India and it ends up in Southeast Asia. And really what's happened here, because the Arabian Plate, India, and Africa are moving northward after the breakup of Gondwana, they eventually close that equatorial seaway called the Tethys. And we see lots of volcanism, crustal deformation, there's earthquakes, there's quite a bit of activity that occurs along this zone. So here's an image showing where the different earthquakes are occurring. And we have some relatively deep earthquakes, some greater than 300 kilometers in here, which telling us that there's something going on, like a subduction. So the ocean floor, or at least the sea floor of the Tethys Ocean, was being pushed down underneath Europe and Asia. The Mediterranean is really the remnant of that Tethys Ocean. The Caspian Sea is also a remnant, and so is the Black Sea. There's actually sea floor underlying these ocean basins here. In fact, here's a picture of those volcanoes in Armenia, overlooking the capital of Armenia, here, Yerevan. And so there's Little Ararat and Big Mount Ararat, but again, big volcanoes related to the collision between this Arabian plate down here and the Europe and Asia. So those two volcanoes lie in Armenia, which is right in this region here. The green here represents the ocean trenches. So again, we're seeing subduction. That's why we have those volcanoes, like in Armenia, and then in Italy we have Vesuvius, and also we have Mount Etna in Sicily there. And then we're seeing again the collision zone between India and Asia, where India crashed into Asia, and then again we have here subduction under Java and Sumatra. But again, all this is related to that Himalayan Alpine orogenic belt in here. The other belt we're talking about is the Circum-Pacific belt, which includes the Andes, the Central American, Honduras, Costa Rica, Mexico here, and then the San Andreas Transform, and then north we have the Cascade Range. Here's that Queen Charlotte Fault in here. Then here's a subduction zone where we see the Aleutian Islands. In 1964, there was that magnitude 9 earthquake over here in Anchorage, Alaska. Huge, enormous earthquake, again, along a convergent margin there. We have the Kamchatka Peninsula, subduction, and Japan. And then as we go farther south, there's the Philippines, the Bonin Islands, Mariana Islands down here, Papua New Guinea, Tonga and Fiji over here, and then we see New Zealand down over here. So they're all part of that Circum-Pacific orogenic belt. Now looking at more detail at the Alpine orogeny, so remember we're seeing deformation from Spain all the way through Europe, Greece, and Turkey, and into the Himalaya and Southeast Asia. And all this really began in the Mesozoic as Pangaea. Remember, Pangaea was breaking up in the Triassic, so we're seeing that as Pangaea is breaking up, we're seeing some of this deformation beginning, but the important events really occur in this Eocene to late Miocene time. In the Alps, here's a picture of some high peaks. These are all over 13,000 feet. And then many of the rocks are folded, again showing that deformation, that compressional forces where Africa is being pushed up against Europe and literally throwing these mountains up in this fold and thrust belt. The Alpine Orogeny, the Pyrenees in Spain, the Apennines in Italy, the Alps in mainland Europe. And your book mentions this complex geology. There's all these thrust faults, and napes are basically huge overturned folds. Like, in fact, you can call this a nape right in there. These overturned folds. There's also maybe a lot of little microcontinents were maybe stuck in there, and eventually there were, if we look at Europe here, so here's Africa. So note that in here there's lots of little land masses in here. So as Africa was moving northward, all these were accreted in a very complex fashion. So microplates are being pushed up in there and making the geology very complex. And so remember, the Mediterranean is part of that Tethys Ocean, and the Mediterranean has these thick evaporite deposits at the bottom, which indicates that there must have been periods of evaporation allowing for these evaporites. And so there's a longer story there that we'll talk about when we do chapter 18. And then when we look at mainland Europe and the Alps, one of the iconic peaks is the Matterhorn. And the Matterhorn is really strange in that the upper parts of the Matterhorn are really part of the African plate, or a huge piece of this African plate. So here's southeast, and we're moving northwest as we go this way. And so there's been all these overthrust faults, sort of like what we saw in Glacier National Park with the Lewis overthrust, where we're thrusting older rock on top of younger rock here. In this case, we're taking this African plate rocks and we're throwing it over Europe in that collisional zone. And so the upper parts of this Matterhorn really are these rocks that originated in Africa, in Gondwana. So here we have a major thrusting event, right, indicating this collision between Africa and Europe. And then in terms of the Himalayas, ocean lithosphere of the northern India plate subducts under Eurasia. So the ocean floor, which is a Tethys Ocean, that seafloor is subducting under Eurasia. We see large plutons form, so we're developing a magmatic arc, an Andean type margin, ocean to continent convergent margin. And the Indian plate finally collides with Eurasia during this Himalayan orogeny around 40 to 50 million years ago. And the key piece of evidence we have here is the rate at which India is moving. So India separates from Gondwana during the Mesozoic, and it starts moving northward. And as it moves northward, we see that the rates are anywhere from 15 to 20 centimeters per year. But around 45 million years ago, the rates slowed down to 5 centimeters per year, which means that right around that time, we're seeing that it's beginning to collide with Asia to form the Himalaya range. High Himalayas, we find that the strata, these are marine sedimentary rocks, and some of them have marine fossils in them. So these were once seafloor sediments that were in this basin, and then they've been, with the collision of India with Asia, they've been uplifted to form a continent-to-continent collisional zone.